Hi, my name is Richard Powell. I'm an audio software engineer. I put together these slides for a discussion group we had at work, and I thought that this would make for a really great talk. I called it the importance of being const. These are slides about what const is, how to use it, what it does, and some interesting sort of side effects of when you use it and what that implies for your code. So I started off with this wanting to make a slide deck more about what const will help you do, and it's actually turned into being more about how to use const. So let's dive into this, and we'll start off with a couple of definitions about const that I've picked up from various books. So starting off, a great quote from Scott Myers in Effective Third, C++, the third edition, not the modern one, but his older book. Item 3 starts off talking about const and how you should use const and why you should use const. And it says, const allows you to communicate to both compilers and other programmers that the value should remain invariant. Whenever this is true, you should be sure to say so, because that way you enlist your compiler's aid in making sure the constraints isn't violated. Okay, cool. That sounds good. And if we also look at some other places in the Google styling guide, code styling guide, it also talks about const. And it says const variables, data members, methods, arguments, all add a level of compile time checking. It is better to detect errors as soon as possible. We therefore strongly recommend that you use const whenever it makes sense to do so. So great sources, great thinkers in C++ telling you to use const. Well, what is const? So if we look into the standard and you read it, what const does, it says a const object is an object of type const, T, or a non-mutable sub-object of such a type. And that's a rather opaque statement, but let's break it down. So, and after that statement, it actually has two examples of how you would use it. You get const T of a T, or a T const T. And they say that these are the same thing. This is where you put your const modifier on your object. And it's a non-mutable. And what does mutate mean? Mutate means to change or to cause to change in a form or value. So declaring an object const means expressions which would modify the object are not allowed. Okay, great. So let's go through some expressions and we'll just play a little game here. This is sort of a little bit of a audience participation. And I'm just asking if you could put a thumbs up if this statement is valid and a thumbs down if this statement is not a valid expression. So, all right, we'll start it off. So I've got my int main. I've declared int in a long const b, and then I have a bunch of statements. So statement 1, will I compile? Yes, great. B? No, lots of thumbs down. Okay, so it is line 3. Great, it's definitely greater than. B, or equal, yep. This statement 5. But I'm just comparing greater than. Oh, right, yeah, it's a typo in the slides, or a typo that you could mean. And this is exactly where const really helps you out. I really did mean greater than equal to. And what about this last one? I'm not modifying the value.
Yeah, but it's still got to create code for it.
It still has to create code for it. That expression is not valid, so that is not a valid expression, even though it didn't actually resolve anything. And you say, maybe the compiler could know that it's not modifying anything and probably optimize that statement away because it knows what the answer is going to be, but the type checking system has to say that is a valid expression, and the type checking system will say that's not a valid expression. All right, moving on, let's try something a little more interesting here. This is one of my go-to interview questions that I'll bring to people. And so I have an array of integers. I have a pointer B, C, D, E, and I've all declared them various versions. So let's try that exercise again. Line 1, valid expression? Thumbs up. Line 2, valid expression? Yep. 3. Some down, some up, some up. That's a valid expression. Okay. Line 4. Okay, so that's definitely thumbs down. 5. Ups, downs, in the middle. Nope, we got a bunch of downs. Right. And line 6, up. And how about the last two? Down and down. 2 thumbs down. So one thing that people do is they often get confused on where does the const apply for these objects. And so the secret for discerning these statements is to read them from right to left. So in that statement, I have P1. P1 is a pointer to int consts or constant ints. You kind of have to rearrange your sentence when you read it that way. However, P2, it's a little easier to read. P2 is a pointer to constant ints. Really easy. And then if we take a look at P3, if we were to read that, P3 is a const pointer to ints, and then P4, a constant pointer to constant ints. And so this is the reason when you read it this way, if you're reading it from right to left, it actually really helps you see why the type preceding the const keyword is becoming the preferred way of writing it. And I highly recommend that's what you start doing in your code, is putting the const after your type. It makes it a little readable, it's easier to discern. So let's pick apart that statement again. A const object is an object of type const t, or a non-mutable subobject of such a type. That's one of the statements I say. And also, what happens is, once an object becomes a const object by the compiler can't really, the compiler is not able to remove the const from that type. It sort of becomes that type. It's a new subtype. That is what that type is. So, once you've said this is a type const object, the compiler can't remove it. And my wife helped me. She came up with this phrase that I'll leave you with, which is, once you are const, you are ensconced. So you can take that one home with you. Well, not entirely. I mean, it's true. People will point out there's a way to get back. You can always const cast or use a regular cast. But I think after we've seen from Bjarne's talk is that, or it was Herb Sutter's talk about how if you're subverting the type system, if you want to cut across the type system, you start entering into a world of danger. So that's where you've opened up the drawer of knives. So we're not going to talk about const cast in this con. So we're going to keep it straight, no casting, no subverting the type system. So what happens is the compiler, when it is doing these expressions to determine if they're valid for assignments, will actually take a look at the type, and it is free to implicitly add const to expressions to make sure that they are valid expressions. So here what I have is I start off with an int d. I'm going to take a pointer to it, and that's fine. That's a valid thing I can do. I'm not changing the types here. When I say assign p2 to pp1, p1 is of type int. It's a pointer to int. It's not a pointer to constant int. However, the compiler can add const to make that expression valid. So that statement is valid. It is allowed to do that. However, it's not able to remove const. And the interesting thing about P3 here is P3 is pointing, you're saying I want to assign P3 to be P2. Now P2 originally started off its existence as being assigned to P1, and P1 was a pointer to mutable ints. And P3 wants to be a pointer to mutable ints, but you can't go through that route. The compiler cannot remove the const from that that type for P2, so that's not valid. But it is able to add const for P4. You're able to add a typed const for. You can make the pointer itself const. It's a free expression that you can do. And the same thing over here. If I originally started off D2 as being a pointer and constant int, you can't remove the constness to it to make a pointer. So error, that will not work. And what holds for pointers holds for references almost. So the whole statement, everything I said was true, except the one expression that's a little odd is R4. So you can't add ref qualifiers to, or you can't add const qualifiers to the ref. It's sort of meaningless. So, huh?
By definition, they are.
Yeah, exactly. That's exactly right. A reference it's a alias for another thing. It is that thing, essentially. And so you can't reseat the reference. You can't change the reference to anything else. It effectively is const. So there's no reason, sort of a don't repeat yourself. There's no reason to say that, or the compiler will actually not allow you to write that statement. So let's go, we'll do our little exercise again. So what I'm going to do now is just a slight change. I am going to create a foo struct, and inside of it's going to have an A and a B object, and A is an int and B is a constant. So let's do that again. So line 1, is it a valid expression? Yes. Line 2, is it a valid expression? Ooh, no. Right. And that makes sense because these are what we said, that the B and the const B are not modifiable. Okay. Because it's a const. What about if I make my struct const? I'm declaring now constant foo. And A? Nope. And B? No. All right. And now let's say I took some pointers. I'm going to take a pointer to F. So now F points to is pointing to foo, and a constant pointer, or it is a pointer to constant foos. And let's do the same thing. Now is A valid? Or sorry, what about line 5? Yeah, and 6? No, pretty straightforward. It's like the same thing as before. What about these two statements? Valid, okay. And number 8? Also valid. So I was, just as one of those things is like, you might not, it's like that one I was trying to catch a couple folks on because I'm actually modifying the pointer itself. And as I had done before, the pointer is not declared const in that one. Only what it points to is const. All right. So what about const through a pointer into a struct? So what I have here is I have just a data member at the top. And I know these are a little bit of contrived examples. Probably in your code you have more meaningful stuff, but I just threw these together for examples. So I have a int on in the static space, and my struct foo will have A, which is pointing to data, and B, which is a pointer to data, but it is a pointer to const int. So, and same sort of exercise. So instead of incrementing the pointer, I am going to actually modify what it's pointing to. So line 1, is that valid? Yeah. 2? No. Okay, right. Now I'm going to say this is a constant foo. Is that, ooh, all right. Well, apparently my slides got mucked up. So how about we move on to line 4, because that's for the next one over here. A little bit out of order. Is line 4, the 4th line, commented valid? No, it's not. And apparently line 3 got skipped. Okay, and then what about line 5?
We see line 3.
We will in a second. My build-in got screwed up. Apparently last minute changes to my slides we're done in haste. I'll get back to you line 3 on it. So skipping line 3 and moving on to line 5. So now at this point we have a pointer to foo and a pointer to const foo. And line 5, is that valid? And line 6? Great. And what about if I label my foo, I go through a const, pointer to constant foo, line 7 and 8. Is line 7 valid? A little bit. It is valid. And that's interesting. What about line 8? Oh, wait. Oh, here's line. Oh, there's number 3. Okay. So line 8. Is line 8 valid? No, it is not. So line 7 is actually kind of interesting when we look at it. So I have declared, so that const pointer foo is actually a pointer to constant foos. But I'm allowed to modify what A points to in it. And that's interesting. What I'm doing here is the structure itself is constant. Yes, I am not actually modifying members of that structure, but I'm modifying things it points to. Keep that in mind. Hold on to that thought. Keep it buried away. We're going to come back to it. But what it is that is interesting, isn't it? let's do some functions where I'm going to pass it pointers. So I have 3 functions here. Actually, well, I have 4 functions, but 3 functions and 1 function with an overload. And so I have function 1, 2, 3, and 3. Yes, I lack imagination when I name my variables. And they take foo pointers or pointers to constant foo. So function 1 takes a pointer to foo, function 2 takes a pointer to constant foo, and function 3 can take either a pointer to foo or a pointer to constant foo. And well, I will in my function have a foo object, a pointer to foo, and a const pointer to foo. Great, cool. So now instead of like valid expressions, tell me if it's a valid expression, and if that's a valid expression, what would it print? So line 1, is that a valid expression? Cool, right. And what would we expect it to print? Func 1? Yeah. How about line 2? No, not a valid expression, so it doesn't print anything. Line 3. Yeah, okay. And what would it print? Function 2. Yeah, that's probably straightforward. And line 4? And what would that print? Function 2. So that actually is a little interesting. I'm going to hold up and take a look at that. That was interesting is, so line 3, I gave it a pointer to foo, or the putter foo, which is a pointer to foo, but there actually wasn't any function I wrote that takes in a pointer to foo for func 2. Func 2 takes in a pointer to constant foo. And this is a point at which the compiler, what it does is it searches through its list of valid functions that it can call, and it doesn't see anything that matches that type. So then it starts manipulating the type of the object and adding things that it can do. It starts going through the list of implicit conversions that's allowable, and adding const is one of those things that's allowable, so now it can resolve that call. And 4 gets resolved because there's no modification needed. It just calls that function directly when it looks for it. So now what happens for line 5? Is that a valid expression? And what would that print of 3? Well, it's going to print 3, but which one? Func 3 star. And line 6? Valid expression, and the const version of it. Yes, that makes perfect sense. Great. Awesome. You guys are doing good. Okay, moving on. So these were a bunch of objects I marked const. It is possible in C++ to mark functions as const. Member functions may be marked const. Sorry, I'll state that again. Member functions may be marked const. Regular functions cannot be marked const. So with that, I have, if you take a look at the syntax for a function, a member function has return value, a function name, any number of arguments, and at the end they say CV qualifiers. And I didn't put it in, but there's also ref qualifiers, but that's for another talk. So let's first examine what happens when you generate functions. And yes, this was from previous slides that it presented, but I just worked so hard on these animations, I want to do them twice. So what happens when the compiler goes ahead and generates code for you? This is not exactly what happens, but it's mostly accurate. So what happens is first a pointer to this object is added as an implicit first argument. Then what happens is CV qualifiers that existed on the end are moved to refer to that object. So you'll see that they get moved. So now my this argument is a constant pointer to constant foos. Then the next what happens is at any place where I would call my member function, it gets modified to take in that f pointer as a first argument. And then all member variables within the member function are prefixed to reference through the this pointer. And then finally what happens is the compiler translates the function into a name-mangled free function through a process called name-mangling, which would be a great topic for a lightning talk. So this is where we had started, and this is where we end up. So what we see is const is through that object. So marking a member function as const means that the this pointer is a pointer to tconst. So that's good. So what that means is the compiler will only allow expressions that will not modify the object. And why is that a good thing? I say it's a good thing, and the style guide says it's a good thing. Why is this a good thing? one of the things that is very important about const is it helps you protect your invariants. And invariants are those conditions that must be true before the function is called, a member function is called, and after the member function is called. They're the characteristics of your object that must be kept consistent. And they are often reflected in the state of your object. So if you modify your member functions unexpectedly, like if you accidentally modified something, you may be mucking about with your object invariants. So const helps you write code that helps you maintain your invariants. So like let me show you a quick example. If I wrote a bad resource handler here, just don't write a resource handler. If you do write a resource handler, don't call it bad resource handler. But so this is a bad resource handler. I'm going to take in a resource pointer or whatever it would be as my R, and I'm going to clean it up when my object gets destructed. And I have a function that does something. And let's just say over the course of time that this code is there, somebody modifies your code. Maybe you modify your code and you accidentally modify your resource, the pointer to your resource. You could either have uninitialized it, you could move it to somewhere else, you assigned it a random value. And what happens is your invariant got violated. One of the invariants of this object presumably is that my resource pointer is pointing to a resource that must be released at the end. It must be maintained valid, so you've broken your invariant here. Now, if I had labeled it const, my error would have been easily caught. This code would not compile because I'm modifying something. Straightforward, const, good. But then const is infectious. So then if you did this, let's say I had do something and said do more work. And do more work itself wasn't labeled const. Then this doesn't compile. Do I really need to add const to everything? Yes, you really need to add const to everything. It is infectious in your code. This is sort of a good infection. This is what you want to have happen. I mean, imagine the bugs you'll find as you go through and label all of your member variables or member functions const that need to be acting const. Or you may find that actually you're calling something and you're doing something decidedly non-const in your function. So what if I write this code? I have two member functions. One of them is const, one of them is non-const. And the non-const version says I'm calling non-const, and the const version says I'm calling const. What will this program print? We take a look here. I have a foo, I have a const foo, and function 1, function 2. And what it prints is first calls the non-const version, then calls the const version. Pretty straightforward. So it sees that A is a const function. It sees that A, if it did the manipulation, if you think about what the compiler does, is it's going to move the A into being the first implicit argument. Then the type of the argument it's taking is a pointer to foo. So that would actually be that first function. And then with B, it's putting it in place, and it's actually a pointer to constant foo. And that would be what the compiler generates for that second function. What about now? I've removed that one. Will this code compile? Yeah, this code compiles, and I get two calls to this. And this is the same sort of thing that we've seen before with when I was passing in pointers. So that function I'm passing in, that A pointer, is a pointer to foo for that value of A, but the compiler is free to add const to it, so it adds const. It looks through first the available functions it can call, it sees that it needs to add const, so it will add const and it calls that function. What about this version? Now I've removed my const version of the function. Does this code compile? No, code does not compile. So a pointer can be promoted to const in this way, so same sort of thing. I can add const when I was going the other way around, but with this way, since B is a, oh, whoops, I copied and pasted incorrectly. That shouldn't be foo this, that should be foo const. But B is a const foo, or is a pointer to constant foos, and you cannot remove that constness. So, all right. So, more valid expressions. This is so much fun. Okay, so we'll do these quickly. Line 1, is this valid? Oh, so before I go on, I have a member function. I've marked my member function as const. I am going to manipulate data. I'm going to manipulate member variables. Is line 1 valid? Is line 2 valid? Nope. Line 3 valid? No. Is line 4 valid? God, I can't do anything to this thing. Is line 4 valid? Yes. Is line 5 valid? No. And is line 6 valid? Yes. Let's take a look at these two statements. These ones were the ones, these are a little more interesting. A is probably obvious, but that line 6 is maybe not as obvious. I thought const meant I cannot modify the object. And this is, we're going to take a little detour into some concepts. There is the concept of bitwise const and logical const. So bitwise const states that this is how member function that is bitwise const can't modify any of the bits inside the object. This is the compiler's view of the const object. It has this object. It views the object as a bunch of bits. And the compiler will make sure that it cannot modify the bits in that function. Logical const it means from the client's point of view that the function hasn't changed anything. Also another way of saying it's observably const. This is sort of, it's not really changing the state of my program through my const function. So if we look back at this one, what happens is I have my object, and my bits are here, and with A, I'm not actually modifying any of the bits in my foo function object. I'm pointing through and modifying the state of the program through my A pointer. And so that's probably obvious because that's a pointer, but it's a little harder to see when I'm doing it through a reference, because a reference is effectively a pointer. So it is actually modifying state of my program through that reference data. So this is something to be aware of. This is something that your compiler won't help you catch because it's sort of unusual. Or not unusual is not the right way to do it. It's non-obvious to the compiler what your intent is. You should strive to make your member functions observably const when you're writing them. You should strive to make sure that this doesn't happen. Okay. What do you need to do when you need to do something non-const in a const member function? So I have my bag of bits. I'm not allowed to modify any of the state and modify the invariants of my object, but there is sometimes where you really do want to modify the members of your objects. And reasons for that could be for caching and for logging. These are prime examples, and they're actually valid use cases. These could be things that you do want to do with your object. So for example, let's say I have a data holder that holds onto a blob of data or a pointer to blob of data or something, and its job is to add more data to my object, and also it calculates a checksum on it. So I can call GetCheckSum, and it'll go and calculate checksum on this object. So I'm also interested in profiling my code. I want to say, well, let me just find out how many times GetCheckSum is called, because maybe that's important for me to audit my code to see how many times checksum is getting called. So I do some work with a data holder, and I'm trying to get the checksum, and error, this does not compile. So, dang nabbit. That const function's getting in the way. What can I do about it? And this is when you would reach for mutable. This is where mutable, it's the oops of the const world. It's the I really did want to modify my data member. It's kind of a C++ wiggle room. So mutable tells the compiler that the value will change even if the function is const. So I can go ahead and do that. Okay, so now I'm good. All right, or am I? Is this code good code? Would this pass your code review? Or this code is potentially toxic. So let's take another look at that. And there is a subtle bug in here. Does anybody see it? There's a race condition. And because of a race condition, or there's a race condition because of threads. So what is a data race? A data race is, in the wordy definition, the execution of a program contains a data race if it contains two conflicting actions on different threads, at least one of which is not atomic and neither happens before the other. Any such data race results in undefined behavior, the dreaded undefined behavior. So to say that in a more succinct way, if two or more threads access the same memory location without synchronization, and at least one is a writer, you will have undefined behavior. And so const means data race free. So const member functions must be data race free. I mean, the reason that they must be data race free is it's sort of a loosely open to interpretation, but I believe what the idea is that the standard does say that it is free to call any of your member functions at any time if they're used in objects. And it actually says it's free to call any of the const member functions of your object. So on any thread. So that means that you need to make sure that your const member functions are data race free. So let's go through and examine where the race condition is, because it may not be completely obvious. So what I have here is I'm going to have my data object holder. I have a global data object holder, and I'm going to call GetCheckSum on two different threads at the same time. And the green bar here represents my threads where they're executing, on which line they're executing. So at one point in time, let's say gdata has never been called, and so it's set to be 0. And thread 1 is on my right and left, and thread 2 is on my right. So let's walk through what happens. So thread 1 goes first, and it goes and it reads in the local variable into a register, or it reads in num times into a local register. Then it gets context switched out, and thread 2 runs, and it reads in the value of 0 into its local register. Then the thread 2 runs, modifying its local register value, and then thread 1 gets a chance to run, and it modifies its register. And then they both go and write out their values. And we see here, when two threads are running, num times was only incremented by 1, even though it was called twice. This is not good. The fix is easy. As it said, add synchronization primitives and to around your data hazard. So this is when, for example, I could add a mutex here. I'm going to lock my function before I call it, and then I will be data race free. And we'll see what happens when I do that. Starting off here, thread 1 runs, it grabs the lock. Thread 2 runs, and it tries to grab the lock, and it can't grab that lock. So then 3 gets to run, finishes to completion. Number times called is incremented to 1, and then thread 2 gets a chance to run, and it finishes, and now num times is 2. So now num times has been called. Great, this is good. Anyone see an issue with using a mutex? Oh, thank you. Did I declare? Okay. Okay, yes, it's mutable. So mutexes are a great synchronization mechanism, but they're a little heavy. They're a little weighty. It's like using a sledgehammer when a little tiny hammer is really what you want to do. But this is the perfect place for atomics. And if you go to CppReference.com, that should be your go-to place for reading about information about the C++ standard library, it says here that the C++ objects of atomic types are the only C++ objects that are free from data races. That is, if one thread writes to an atomic object while the other thread reads from it, hey, that sounds like exactly what we're doing, the behavior is well defined. Great, cool. I am going to reach for a standard atomic here. And what would happen in this case? So here what happens is thread 1 goes first, and atomic increments are well defined on different threads. So even if thread 2 comes across and runs and hits that same line at the same time, your processor synchronization mechanisms or other things will guarantee that atomic increments are well defined across different threads. And then they both return, and number times called is equal to. Great. So one thing to note, though, is about that is mutexes and atomics are a good synchronization primitive, but they are not copyable. So you might think that, oh, great, I want to do this change. I'm going to add an atomic int, or I'm going to add a mutex, and suddenly your code may break in other places because now you have made your objects non-copyable. So be aware if you start using these primitives that you have to consider perhaps making your own copy constructors, which is probably not a good idea. In fact, actually, you may want to bury those synchronization primitives into smaller objects that have defined copy constructors that you can then use. So what if I want to accelerate my code, if you will? Like, what if CppCon was very expensive? How could we speed things up? So before I said that there were logging and is a great way of using Mutable, and another valid use case would be caching. Well, this would be a great idea. Let's go ahead and add caching. So the idea being is, instead of calling GetCheckSum, I'm going to first check to see if I have saved off a previous calculation. I'm then going to use that previous calculation if I have. Otherwise, what I'm going to do is I'm going to calculate it, set the cache to be valid, and then anytime I invalidate my object, I add more stuff, I'm going to invalidate my cache. I'm going to mark it as false. And so this is a great way, this is a common pattern people use to add values in there, except that const now is getting in the way. Same way with my incrementing, const is getting in the way here again. So, mutable, I reach for mutable. And there I go. I add mutable to my things, and now the code compiles. Are we good? Does this code have any problems? Again, potentially toxic code. I forgot atomics. There, I'll use atomics. Oh, and right because I have atomics, I'm going to add a copy constructor, and probably I should be adding a lot more things. If I'm writing a copy constructor, I suddenly have to invoke rule of 4 or rule of 6 or rule of 7, or I forget how many I'm supposed to do. But for the examples of this, let's assume I've done everything right, but I add a copy constructor. So now, am I good to go? Deadlock. I don't know about deadlock, but it's still dangerous code. This code still has a race condition. Okay, so if you look at your code here, and let's say that I had one thread where I was getting the checksum, and another thread where I'm adding more data. This is a race condition. This is a blatant race condition here, but that's fine. I mean, I'll say that's fine because this is actually an expected data race condition. I have two threads, one of which is a reader and one of which is a writer to the same object. So that's not a data race condition problem in my code. That's a data race condition because the client is using it wrong. They're holding it wrong, if you will. They're not supposed to do this. And the reason that I say that that's okay that they've done a problem is because I have clearly marked my const functions as const. They are read-only functions, and if a client is using a read-only function at the same time they're using a write function, they're going to have some problems. So that's not what I'm talking about.
But it doesn't have to be the same client, right?
It could be different clients. Sorry. Right, but it's sort of, but it would go with anything that someone would do on, sorry, the question was, they don't have to be the same client. This is true. But if you have any part in your code where you have a reader to your value and a writer to your value, you're going to have a problem. And that is sort of, that's a higher level problem. I'm saying that's a problem to the clients of your code. It could be the same code that's doing it. Well, actually, I don't know how the same thread would call it twice. It can't. But if you had two threads and they were at different parts of your code, and like one part of your system grabbed a library and another part of your system grabbed your library object, and then they both modified the same thing, then you probably have a problem in your design.
Right,
but
well, either you do it internally in your API, so it does self-locking, so it prevents that, or you were imposing it on your clients.
Right, yeah. Yeah, exactly. Like if I said that this is valid, I could have written my code to be lock-free. Or I should say, I could write my code to be thread safe. And when I say, and I should clearly mark that in my documentation, saying, yeah, these functions are valid to be called together. But if you had a const member functions, if you have 3 or 4 const member functions, and they aren't, and they're all const, and it is not thread safe, that's unexpected to the client. That's the point I'm trying to make. So let me illustrate the data race condition I said that existed in that code, why I have some toxic code there. So I'm going to call GetCheckSum on one, I'm going to call GetCheckSum on the other, and let me expand what that actually would do. So we see that thread 1 on the left is going to, first it checks to see is it cached. If it's not, set it to be true, calculate the checksum, and then return it. And conveniently I put up there so you can see what it looks the data members inside of gdata on the upper right-hand side. So first, both threads enter. Thread 1 proceeds. So it checks to see the cache. And it says, oh, no, this data holder, the cache is not set. So then it proceeds. And it marks the cache as true. Now, unfortunately, at that moment, it gets swapped out, and now thread 2 proceeds. And it checks to see is the cache valid. Yes, the cache is valid. Great, I'm going to grab that value, and I'll return. Oh, no. Thread 2 returns the mCache-checksum before thread 1 has a chance to calculate the answer. So it returned the wrong value. Eee. So the issue seems to be that cached and cache-checksum are in the wrong order. So what I mean by that is if we look at the GetCheckSum function, I first check to see if it's cached. If it's not, I will set it to be cached, and then I calculate the value. So now, there, I fixed it. Are we good? Oh, still dangerous. Ugh, well, okay, let's walk through that again. What do I mean by dangerous? Let's walk through. So both threads enter. mCache is false. First of all, it calculates the checksum. Then thread 2 proceeds, and it calculates the checksum. Okay, both call GetCheckSum. All right, then it returns. It sets the cache to be true, and the other one sets the cache to be true in the return. So the atomics are synchronized, so there's no issues on both threads writing those values. They both eventually return the right answer. I'm assuming that calculate checksum is also thread safe. Work with me, guys. Let's just make that assumption. So what's the big deal? I mean, it got the right answer. I mean, it did do more work than it needed to do. I mean, what if it was 2 threads instead of, or if it was 100 threads and they all did this exactly at the same moment? Then they would all end up calculating that, and that might be really expensive. Or what if the calculate was super expensive? What if it took like 5 minutes each time, and now I have 2 threads blocked essentially for 5 minutes? I would say that's functionally correct, but that's not the problem I have. There's another pernicious bug lurking in here. And can you see it? All right. No, adding more data is fine. Well, fine is not quite fine, but I would argue that that is a race condition from the client. Sort of, if it's sort of an external thing is modifying it. And so the problem I'm saying is if I were to access this object only through its const functions, I still have a problem. Very good. All right. So this is this is case 1 I worked through, and we went through that, and it's fine-ish. It may take a lot of time. It may do extra work, but it's still okay. What about this case? And this is the one you might not think about. This is the one you probably don't ever think about. So I have thread 1, which is just going to call GetCheckSum, and then thread 2 is making a copy of my object. All right, let's go ahead here and walk through what happens. So assuming the checksum has not been set, thread 2 now proceeds. So it actually hasn't been set, so its data members are unknown. So then what happens, first of all, it goes ahead and reads in the cache checksum, which has been 0. It's the default. Now thread 1 proceeds. It does all the work. It calculates the checksum, and then it finishes and sets the cache to be true. Thread 2 now gets a chance to run. It reads in and says, oh, my cache is valid. But the calculate mCache checksum is incorrect. This is a horrible race condition. So the order of initializations of the copy constructor caused this subtle issue. So I would point out this is not actually a data race. This is more of a race condition. This happens when you have any 2 data locations that must be synchronized. I don't have a data race here. I'm not modifying the same data location by 2 threads. I'm actually modifying different data locations that must be synchronized. So there, I fixed it. Did I? I changed the order of mcached and mcached checksum. And then I changed the order of initialization in my copy constructor. Am I good? Oh, it's okay. But it's very brittle. In fact, actually, I'm not even 100% sure this is correct. But this is scary code. I mean, how well will this be maintained? How do you even test this type of code? So. Switching gears for a little bit. We talked a lot about that. Let's go back to Const. And another question. Does Const generate faster code? We just had a great presentation by about C++ and efficiency, and we love efficiency. But does using Const generate faster code? Generally, no. I mean, when it comes to optimizations, Const is still principally useful as a tool to help us as the class designers better implement handcrafted optimization than for the compiler to do something special with it. And let's look at a little example. Let's go through this. And let's say I have a logit function and a modify it function, and I have foo. And foo is going to take in a reference to const A and a reference to B. I really do have a problem with my variable names, A and B. I should probably fix that. But first of all, I'm going to log my value. Then I'm going to modify a completely different value. And then I'm going to log it again. I'm going to log A twice. So then we take a look at the assembler. Let's take a look at what the assembly instructions that this produces. And so what we see here is, first of all, it loads and I compiled this with -o, and it loads B, then it calls logit, then it loads in, sorry, that should say loads A. Sorry, so read that as loads A, then it calls in to modify it, and it has to load A again. It did 2 loads. And by the way, if you ever want to take a look and you've got your laptop or your phone and you really want to take a look at the assembly, there's a great website I use all the time is godbolt.org. There's a number of other sites to look for assembly, but if you really are in a pinch and you have only your browser on you, this is how you can take a look at some assembly code. Anyway, going back, I see that there were 2 loads to, well, it should say A, but it says B. So 2 loads. I must not have set my compiler values high enough. Let me crank up the optimizations to level 3, and that should get rid of that double loads. It should only need to load it once. No, the compiler still generates 2 independent memory loads. Why is that? Huh? Aliasing. The compiler can't make any assumptions about what happens around the function calls. Like, it doesn't know what's happened outside of it. It only really sees that these are, we see them and probably think of them as 2 different values, but the compiler's like, no, they could be the same value. For instance, someone could have written that code on the right there. So your compiler has to be very conservative about those things. So even though you think that using const may help you with optimization, it's not really principally a tool for optimization. It's a tool for writing good code. So to review, const. It helps you find your bugs at compiler time. It makes it easier for you to reason about your code. It helps you preserve your class invariants. I would also, when I mentioned I was doing this talk, people were like, please, please, please have people start using this format for writing their values. And I agree. I think actually it's a little difficult. I had to go through my slides several times to get it, so I'm adopting this practice. But I would recommend start writing your T, const, and then your variable name. Const member function should be observably const and thread safe. And also, const doesn't necessarily make faster code, but it makes more correct code. And as we all know, it is far easier to make correct code fast than fast code correct. And questions? So my friend here will go around as you raise your hands and he'll give you the microphone. Any questions?
Just a question about the const of the getters, the read-only. And you say that they have to be data race free. Obviously, threads are new in C++11. We're just getting to them. So my question is, if your object's only being accessed, you know it's only going to be accessed by one thread because the way you structured your program. Do you even have to worry about it because the compiler is not going to create another thread for you?
This is probably true. So I guess I'll say it as you're saying. If I know that I'm only going to be executing on one thread, do I have to worry about thread safety? I would say code tends to live in places you don't expect it to. Your code that you've written may end up somewhere else. And granted, you might not be writing in a multi-threaded environment today, but you might tomorrow, and maybe it's good to have practice at writing the code. Writing thread-safe code is very hard, and data race-free code can be hard. But I think for the most part, this only starts becoming a problem when you start reaching for mutable. And when you start reaching for mutable, you're doing something unusual in your const functions. I would say, I think 99% of the time, I've never used the word mutable for const. And I can write pretty good observer code, because generally, really, I'm just, for my accessors that are const, they're really just going to get something. They're just going to get a value. They're not really modifying things. And then on those small cases of time, when you do reach for mutable, that is now, because you've reached for mutable, you should really think about, what am I trying to do here? Where will this code live? Will it be thread safe? How do I make it thread safe? Perhaps actually it's better to create, so my cache example, that could be great as a cache object whose job is to synchronize itself and is, got lots of scrutiny and people looking at it. So I guess my answer is for you is be aware that your code today may be one in a single thread, but tomorrow it may not be. So you should consider thread safety.
I like using the pointer to implementation pattern once in a while, but it doesn't really respect constants because of the reasons you mentioned earlier. Yeah. Any ideas?
So I've seen people implement sort of an entire interface through that. It's actually, what they do is they end up repeating themselves completely within there, and but it's hard because you're right, because you end up going through this pointer and the compiler sees I haven't modified anything in here, so it's really up to you. And I think actually this might be a reason to avoid trying to use the pimple platter, but it is a useful thing for ABI compatibility. So I don't have a good answer for you. I'm curious if anybody else does, who uses const or pimple. That's a great question.
The questions?
I'd say for the pimple pattern, one thing you can do is you could, rather than accessing the pointer directly, add a couple member functions that you always use, private member functions that will forward the pointer back to you, and then your const one can forward you the const t star or whatever. It's similar to what vector does. Vector gives you const iterators when you call const, even though technically it kind of could have given you just a plain old iterator.
Any other questions? Well, all right. Thank you all.